Welcome back to Physics Fundamentals. In this video, I'm going to revisit the concept of net force, which we previously studied in the case of one dimension, and extend it into working with vectors and two dimensions. Let me get my head out of the way, and let's start drawing some pictures. Whenever we're talking about forces, we're generally going to be invoking Newton's law in some way, shape, or form. We've seen previously that if we have several forces, we can add all of the forces together to get a net force. And we are now talking about making our force a vector. So if we have a vector force, mass is always a scalar, but acceleration can also be a vector. And while vector equations are always intimidating at first, the nice thing about a vector equation is that you can actually break it down into components. The net force in the x direction is equal to mass times acceleration in the x direction, and the net force in the y direction is equal to mass times acceleration in the y direction. And by breaking things down like that, we can look at each part individually and start trying to deal with it. There is a lot that we can do with forces in two dimensions. We can start modeling projectile motion and things that are happening in 2 and 3 dimensions, which is a little bit beyond the scope of this course. In this course, I am specifically going to be interested in situations that are in what we call static equilibrium. An object in static equilibrium is an object where the velocity is equal to 0 and the acceleration is equal to 0. Compare that to dynamic equilibrium, where the velocity is not actually 0, but the acceleration is still 0. In either case, an object in motion remains in motion at a constant speed. An object at rest remains at rest at a constant speed. The force is equal to 0. And so that's something that I want to think about. Let's consider an object on an inclined plane. Let's go ahead and set this plane at 30 degrees. And let's say that this object has a mass of 2.50 kilograms. Well, what forces are acting on this object? I've got the force of gravity pulling it downward. I've got the normal force all of a sudden not pointing straight against gravity, because the normal force points perpendicularly to the surface the object is resting on. And then I've got the force of friction. That's probably enough forces here. And let's say that I know that this object is in equilibrium. That means that the net force is 0. And I can work with the net force in components separately. All of the components have to be 0 in and of themselves. The components here, at first glance, are going to be kind of annoying, because we would normally draw our x-axis and our y-axis which means that the force of friction is going off at a 30-degree angle, and then the normal force is going off at a 120-degree angle, and that doesn't look like a lot of fun. My favorite trick in physics is that we don't need to do that. What if I set up my axes so that the x-axis was pointing this way and the y-axis was pointing that way? Just turn your page. Turn your page a little bit so that your x and y axes look like they are pointing in the right directions. Now the friction force is just in the x direction, the normal force is just in the y direction, and the only one doing something weird is gravity. All right, well, let's examine that a little bit more carefully. If I tilt this plane, the inclined plane, so that the top is horizontal, then that means that the bottom is going off at an angle and the force of gravity is going off at an angle. I know the angle in question. I know right here is 30 degrees. I said I was going to draw this bigger, and then I realized I didn't actually draw this much of any bigger. Let's try again making it bigger. Bigger is better. There we go. Force of gravity is now going off in this direction. I've got 30 degrees. This is my x-axis. This is my y-axis. What is that angle going to be? Well, properties of right triangles. I've got a 30-degree angle, I've got a 90-degree angle. The only angle that's left is 60 degrees. So 180 degrees gets me halfway around the circle, and then another 60 degrees gets me to the gravity. All told, that's 240 degrees. The magnitude of the gravitational force is the mass times gravitational acceleration. The mass I just scrolled off the screen is 2.50 kilograms. Gravity, we know, is always 9.80 meters per square second. And when I multiply those things together, I get 24.5 newtons. But now, I need my components. The x component is the magnitude times the cosine of 240 degrees, because I've gone and figured out what that angle is in standard position. So 24.5 times the cosine of 240, my calculator tells me, is negative 12.25 newtons. And then the y component would be Fg times the sine of 240, which my calculator is happy to tell me is negative 21.2 newtons. And I should come back up here, because I only have 3 significant digits. I can't call that 12.25. I have to call it 12.3. All right, so we've done some calculations. I'm now going to redraw my figure. I've got my x-axis pointing this way. I've got my y-axis pointing that way. I've got the force of friction pointing this way. I've got the normal force pointing this way. And I've got gravity pointing that way, which I've just broken into components. The x component was 12.3 newtons, and the y component was 21.2 newtons. Now, because I know that my object is in equilibrium, the net force in the x direction, which is the force of friction and the x component of the force of gravity, must be equal to 0. Which means that the force of friction must be 12.3 newtons. And likewise, the net force in the y direction, which is the normal force and the y component of the gravitational force, must be 0. Which means that the normal force must be 21.2 newtons. Looking at the big picture here, there's a number of things that we can do with this information. If I didn't know that this was in static equilibrium, I could still find the normal force because I know it's not floating up off of the plank, and I could use that to get information about the frictional force. Or just knowing the normal force and the frictional force, I can get some information about the coefficient of static friction. But for right now, just understanding the relationship between these vectors is good enough for us. This process kind of highlights one of the things that can be very interesting. Remember that the resultant is the solution to vector addition. When we're dealing with forces, there is another quantity that can be interesting. It is called the equilibrant. Equilibrant. The equilibrant is a new force that you add to a system that you have analyzed, which will put the system in equilibrium. So if you have an object, and there are a couple of forces acting on the object, the resultant force, kind of remember the head-tail approach. If I take the tail of the one vector and put it at the head of the second, I get an equilibrant that is going kind of in this direction. Or, yeah, the resultant, which is going in that direction. The equilibrant is a force that is going in that direction, which will balance things out so that the net force is 0. All right, so if I add all of my forces together, I don't get 0. But then I add the equilibrant to that, I will get 0. Which means that just doing a little bit of algebra, the equilibrant, I should have done that the other way, sorry about that. The equilibrant is the negative of the net force. Just doing a little bit of algebra to rearrange the equation. And the net force is itself the resultant from adding forces together. So let's take a look at a particular example. Let's say I have a force that is 1.35 newtons at 42 degrees. And I have a second force, which is 2.13 newtons at 133 degrees. I can rewrite these forces as components. F1 as components is going to be 1.35 newtons times the cosine of 42 degrees for the x component, and 1.35 newtons times the sine of 42 degrees for the y component. And the second force will be 2.13 newtons times the cosine of 133 degrees for the x component, and 2.13 newtons times the sine of 133 degrees for the y component. Grabbing out my calculator, I can work through those calculations. The first vector has components 1 newton, 0.903 newtons, and the second force vector has components negative 1.45 newtons, positive 1.56 newtons. All of these are vectors and they should all have hats. From that, my resultant vector, add those two things together. 1.00 minus 1.45 is negative 0.45 newtons. 0.903 plus 1.56 is 2.46 newtons, rounding to the nearest hundredth of a newton, which was my worst precision there. And I can find the magnitude. Well, it'll be the square root of negative 0.45 newtons squared plus 2.46 newtons squared. And the angle is going to be the angle whose tangent is the y component divided by the x component. I've mentioned in previous videos, the negative here doesn't really do anything. If you leave it off, that's fine. Over here, that's where things get really weird. So I want to stop and think and realize that this is going to be, well, it has negative x, positive y. This is going to be an angle in the second quadrant. So I'm going to leave that negative out as well when I punch this into my calculator. The magnitude comes out at 2.5 newtons. I am down to 2 significant digits at this point. But then the angle. My calculator tells me that the inverse tangent of 2.46 divided by 0.45 is 79 degrees, or 80 degrees. But that's the angle right there. The angle I want to report is the angle here, which would be 180 degrees minus the angle that came out of my calculator, which is 80 degrees. So My resultant in this case is 2.5 newtons at 100 degrees. But that's not the only thing that I might want, because the resultant tells me the sum, but if I want to balance this, then the thing I'm really looking for is the equilibrant. And the equilibrant is the negative of the resultant. This is easier to figure out if you go back to the components. Instead of negative 0.45, it's going to be positive 0.45 newtons for the x component. And instead of positive, it's going to be negative 2.46 newtons for the y component. This is also why setting up your tangent like this and not using the negative when you punch it into the calculator is so important. Because if you set this one up, you would get the same value coming out there. But in this case, positive x and negative y means that we want to be down here. That's where our 80-degree angle is going to be this time. So we need 360 degrees minus 80 degrees, which comes out at 280 degrees. So the equilibrant is going to be 2.5 newtons at 280 degrees. All right. In theory, nothing new in this lesson. A little bit of new vocabulary with this equilibrant that I've been talking about. So again, a recap there. The resultant is what you get when you add all of the vectors together. When those vectors are forces, the resultant is the net force on the system. The equilibrant is the vector you add to all of the force vectors you have so that the net force becomes zero, so that the system is in equilibrium, hence the name. But the equilibrant is always going to be the negative of the resultant. The terminology here is not all that important. You should be able to find a net force, no problem. In the upcoming work we're going to be doing, we're going to be looking at equilibrant forces and using that as a way of testing our calculations. But in the long run, it's not really something that we put a lot of effort and emphasis into. So pay more attention to the pictures and the understanding of how these forces are interacting than you necessarily do the names of everything. Right. For now, though, I think that's far enough, so I'll wrap up with that. As always, thank you for joining me, and I'll see you next time.